I'm here to talk to you about truth, and specifically how a mathematician thinks about truth. And I'm going to start off by talking about the course that was either your favorite or your least favorite math class in high school. It's probably not in the middle. It was probably either your favorite or your least favorite. If it was your favorite, my office is in the first floor of the science building. You should come see me and we'll talk about the math major. If it was not your favorite, it's still the same place, and we could still talk about the math major because you need to know why this is such a beautiful topic. So come see me about the math major. I'm going to talk about, if it will move to the next slide, and it doesn't appear to want to. There we go. For the majority of the history of thought, in mathematics, geometry was the repository of truth. Geometry told us true things about our world because we could look around and it seemed to fit geometry. It originated in Egypt because in Egypt the Nile floods every year. And after the flood, all your familiar landmarks are gone, and you've got to resurvey your land to figure out where your property is in relation to your neighbor's property. And geometry was a very important part of that. Now, the geometry that the Egyptians used was really just a list of rules, and they weren't always 100% correct. So starting in the 6th century BCE, the Greeks said, you can't just find rules that seem to work. You've got to be able to find things that work and that you are able to prove that they work logically with rigorous deductive reasoning. You've got to be able to do that for us to accept that something is true. And so the Greeks had this great tradition of finding geometric facts and proving them to be true. If you took high school geometry, you probably had to prove that things were true. And about 300 years later, the mathematician Euclid produced what is one of the most important books in intellectual history. It is called Elements. It's actually not a book. It's a collection of 13 books. They're often bound together in a single volume because it's not very long. And it's called Elements. And he took all of the geometry that was known at the time that he could gather up and put it all together in one place. And it is one of the most widely published and translated books in the history of thought. Second only to the Bible, really, is the fact that Euclid's Elements was so important. The geometry that you studied in high school was really based on Euclid's Elements. So what Euclid did was he insisted upon proving everything that he said about geometry using something known as the axiomatic method. The axiomatic method consists of 4 parts that I'm just going to touch on briefly. The undefined terms, those are things we don't define, usually point. Everybody knows what a point is, we're not going to define it. Line, plane, these are things we know. Then we start making some definitions. What other things do we need to talk about besides points, lines, and planes, and how can we define them? Then what I'm going to spend some time on here is the axioms. These are the hopefully clear and evident things that we can look around and say, yeah, that's true. We all know that's true. We can tell that's true. And then we start proving things. We give statements. We tell you what the reasons for those statements are. And we make a proof of a fact. And we call those theorems. Now, Euclid, in his whole collection, 13 books of Elements, used only 5 axioms. And in geometry, you often call those axioms postulates. You probably called them postulates in your high school geometry class. There were only 5 that he used. And his first one is, and I'm going to read it the way it was translated by Heath from Euclid's Greek writing. The first postulate is to draw a straight line from any point to any point. You know this one. This one is the one that says any 2 points determine a unique line. So you've got 2 points, P and Q. You can draw a line between them, and you can only draw that one line between them. There's not another line that goes between P and Q. His second postulate was this: to produce a finite straight line continuously in a straight line. And to translate that into modern English, if I have this line segment PQ up here, I can extend it infinitely in either direction. And most of you are looking at these things I'm telling you right now and thinking, yeah, that's true. Of course you can do that. All these things are true. The third one is to describe a circle with any center and radius. If I pick any point and say I want to make a circle with that point as the center, and I want it to have radius 7 centimeters, well, I can do that. I can pick any point I like anywhere and draw a circle with any radius that I like. And you're thinking, yeah, of course, you can do that. Yes. His fourth postulate was that all right angles are equal to each other. A modern mathematician would probably prefer the word congruent to each other, but all these right angles, no matter where they are, here, there, over there, they're all the same. That's Euclid's fourth postulate. And once again, that's another one that, yeah, that makes sense. Postulates are supposed to make sense. We're supposed to all just look at them and say, that's true. Yeah, I believe that. And then we start proving theorems later. That was 4 of them. Euclid's fifth one is a little bit different. First 4, we're all thinking, yeah, I believe these things. They appear to be true about our world. I think those are okay. His fifth one was fairly controversial. And historians of mathematics think that Euclid didn't even really like his fifth postulate because he put off using it. He didn't want to use it, it doesn't look like, until he absolutely had to. Here's his fifth postulate: that if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than 2 right angles. I don't think that one is as obvious as the other 4. First off, the first time you see that, or maybe even the second or third time, you're still staring at it thinking, what? What all does that say? That is not at all obvious. It is quite different than the other 4. The other 4, we look at them, we say, yeah, that's true. That appears to be true about our world. This one we look at and we think, I don't even know what that means. There were early criticisms about this from the other ancient Greeks, like, that shouldn't be a postulate. That one is too complicated. We need to see if we can turn that postulate into a theorem. Instead of making it something that we just say, yeah, that's true about our world, let's use those other 4, the ones that we all agree on, the first 4. Let's get out our geometry thinking hat and prove that that 4th one is a theorem, that it follows. It's not a real simple thing. It lacks, as Proclus said, the special character of postulates. It's just not simple and pithy and something we just understand by looking at and thinking about it and saying, yeah, that one's true. This one, the 5th one, that one. It's hard to even tell what he's saying there. So for the next 2,000 years, geometers and mathematicians set out to prove that fact. Let's just use the other 4. Let's ignore that 5th one. Let us prove that the 5th one is a theorem. That is true because we can prove it to be true, not because it's something that we all just agree is true about our world. Every single proof that was presented had one of 2 flaws. It was either a mathematical, logical kind of flaw, like that doesn't hold, or that argument right there is invalid. You can't use that one. Or the other flaw that was very prevalent was that in order to prove the 5th postulate, the geometer might assume the 5th postulate. Well, of course, if you assume it to be true, you can prove it to be true, but that's not a very good mathematical proof. You're just assuming it to be true. So every proof had some sort of flaw. For 2,000 years, no one could prove the 5th postulate. Here's how you learned the 5th postulate in high school geometry. When I write it like this, it probably makes a little more sense to you. You can probably believe this one. Given a line L, the bottom one, and a point P not on L, the red one at the top, there exists a unique line M passing through P that is parallel to L. If I got a line, put another point somewhere that's not on that line, I can draw a line through there parallel, and Euclid's fifth postulate says that's the only line that goes through there that's parallel. There's just that one. That one seems a little more reasonable. I'm going to go through this really quickly. Here is one of the more famous people who tried to prove that fifth postulate. That's an Italian priest, Girolamo Saccheri. And he studied these quadrilaterals. If you recognize the markings on them, the bottom two angles are right angles, and the two sides on the right and the left are congruent to each other. And I often ask my math majors in Math 306 to prove that the top two angles, D and C, are therefore congruent to each other. They have to be the same. We'd really like to say that they were right angles, but all we're able to say is that they are the same. And so Saccheri said, well, I know they're the same. I want them to be right angles because if they are right angles, then Euclid's fifth postulate has to be true. I have proven it. He said, I want them to be right angles, so I'm going to say, well, let's look at what happens if they're not right angles. What if they're acute angles? What if they're obtuse angles? What would happen? Well, when Saccheri said, what if they're obtuse angles, he quickly reached what is known as a contradiction. He said, they can't be obtuse angles because this other thing happens that we know cannot happen. So we're going to dismiss the obtuse angle, and we're going to say, well, that happens when I'm looking at that Saccheri quadrilateral there, and those angles at the top aren't right angles, they are acute angles. What happens? Saccheri was hoping to find another absurdity, something that just we all knew wasn't true, but he could never find one. He found all kinds of weird things, but he never ever found a contradiction, so he just gave up. And he finally just wrote in his book that the hypothesis of the straight angle is false because it's repugnant to the nature of straight lines. In other words, he said, it just can't be true. We know it can't be true. It just doesn't make sense. If he hadn't done that, we would study Saccheri as the father of what is known as non-Euclidean geometry, but he just dismissed it. He said, it just can't be true. I'm getting some weird stuff, and I don't like this weird stuff. After another century or so, mathematicians finally got to the point where they were ready to consider what might happen in the case that those other angles were acute. Three mathematicians in particular, Janusz Bolyai, Carl Friedrich Gauss, and Nikolai Lobachevsky, did studies of geometry in which this different postulate held. Not Euclid's fifth postulate, but this one. There exists some line somewhere and a point that's not on it, so that there are two lines through that point that are parallel to the first line. That's not what you learned in high school geometry. This is a totally different axiom. Turns out that if you take this axiom, then you can do some pretty legitimate geometry. It's just different geometry than you learned in high school. In high school, you studied Euclidean geometry. This is non-Euclidean geometry. It doesn't match what Euclid did, but it turns out to be a perfectly reasonable geometry. Eugenio Beltrami, in the middle of the 19th century, found out that he could put a model for this non-Euclidean geometry inside of the old Euclidean geometry that everyone knew and establish what is known as the relative consistency of non-Euclidean geometry. Anything that goes wrong in non-Euclidean geometry already goes wrong in Euclidean geometry. So there will never be a proof of the fifth postulate because the fifth postulate could be considered true and you could get a very valid kind of geometry known as non-Euclidean geometry. This devastated mathematical thinkers. Geometry was supposed to be true. We're supposed to be finding things that are true in geometry about our world because those postulates seem to be true about our world. And all of a sudden, Euclid, who was the high priest of mathematical truth, we discovered that there is not necessarily the indisputable truth in Euclid that people thought there was. And if there can be non-Euclidean geometries, what else might be happening in math that we don't know? Maybe truth is more than what we see in the world around us. Maybe just because we can look around this world and see truth in the Euclidean geometry as they thought, maybe truth isn't necessarily only found by looking around our world. So what is mathematics even about? If non-Euclidean geometry can be valid, how do we know anything about math? How could anything possibly make sense? What is math about? I'm going to stop here for just a moment and tell you non-Euclidean geometry, the geometry that's not the geometry you studied in high school, the one that has multiple parallel lines through the point, turns out to have multiple real-world uses. You can use it in physics, in studying the cosmos, computer science. You can use it in art. The projective geometry artists use is a non-Euclidean geometry. You can use non-Euclidean geometry in geography. So even though it didn't appear to be true about the real world, it turned out to have lots of valid uses. So mathematicians set out to let's make mathematics true again. Let's pin it down. Let's make sure that we're not going to have any weird stuff. Let's get rid of all the weird stuff. And they set about to make mathematics have a solid logical footing, that we would be able to figure out everything we needed to about mathematics logically. If it was true, we could prove it. And if we could prove it, it was true, and those two things were the same set of things. True things, things we prove, all together. Bertrand Russell, in Principles of Mathematics, 1903, says that the pure mathematics, what is math? Well, pure mathematics is the class of all propositions of the form P implies Q. I'm not going to read the rest of that, but P implies Q. That's a logical thing. That's logic. If P, then Q. 2 pages later, Russell says that the fact that all of mathematics is symbolic logic is one of the greatest discoveries of our age. In other words, instead of using logic, mathematicians thought, we're not going to use logic to study mathematics. We're going to say that mathematics is logic, and what we're going to study is logic. Mathematicians study logic because that's what math is. That's where we find truth, is in logic. Truth is logic. Let's go from there. A German mathematician, Gottlob Frege, started trying to codify this fact, that all of mathematics is symbolic logic. If it's a fact in math, then it's either a law of logic or I can prove it using logic. That's it. Math, that's all math is. So he wrote this huge, multi-volume work, the Grundgesetze der Arithmetik. And he started developing his ideas. He started with the idea of a set, a collection of things, and went from there and said, look, everything that's true, we can prove it. If it's true, we're going to prove it. We're going to use logic, everything that's true. He put this basic law 5 down here. I've printed it for you up here in a modern formulation. I'm not going to read it to you, but you can see at the bottom, that's basic law 5. And most mathematicians would look at that basic law 5 and say, well, that makes sense. That doesn't appear to be controversial. Basic law 5? Oh, yeah, okay, I'll take that. Basic law 5 makes sense. It looks fine. However, in 1902, Frege got a letter from Bertrand Russell pointing out an issue he had discovered with that basic law 5. And like most mathematicians, Russell said, I used to believe it. This I formerly believed, but now this view seems doubtful to me because of the following contradiction. Let W be the predicate to be a predicate that cannot be predicated of itself. Now, that's a lot of math words, and I'm going to make it easier for you here in a minute. And the question he asked is, can W, this thing he just defined, be predicated of itself? And if you take this sentence that I just read to you, that probably doesn't make a lot of sense, you really have to read it very carefully, and you apply basic law 5 to that sentence to answer the question, can W be predicated of itself? If you answer yes, you can use basic law 5 to prove that the answer is no. And if you answer no, you can use basic law 5 to prove that the answer is yes. So if the answer is no, the answer is yes, but if it's yes, it's no. That appears to be an issue with math. Here is a way that maybe you can understand basic law 5 a little easier. You may have heard of this before. This is called the Barber paradox. It is a form of Russell's paradox. It's a little easier to understand. We've got this village. And in this village, there is a barber who shaves everyone in the village, and only those people in the village that don't shave themselves. You've got this barber, got this village, and in this village, the barber shaves all the people that don't shave themselves. You've got two choices. You shave yourself, or the barber shaves you. There's no other option in this village. Everyone fits into one of those two categories. They either shave themselves or the barber shaves them. So, does the barber shave himself? Who shaves the barber? Who is it? Who is shaving the barber? Well, if the barber shaves himself, and let's remember who the barber shaves. The barber shaves the people that don't shave themselves. So if the barber shaves himself, he's one of those people that don't shave themselves, because that's who he shaves. So if the barber shaves himself, he doesn't shave himself. Because the people the barber shaves don't shave themselves. So we have to say maybe the barber doesn't shave himself. Well, who does the barber shave? The barber shaves all the people that don't shave themselves. So if the barber doesn't shave himself, he's one of those people, so that means the barber shaves himself. Either way, if you say the barber shaves himself, then you can conclude the barber doesn't shave himself. If you say the barber doesn't shave himself, you can conclude that the barber does shave himself. Either way, that is essentially the same thing as Russell's paradox here, applying basic law 5. To find a paradox like that in the middle of mathematics was devastating. Frege was shaken. He was horribly depressed, mostly for the rest of his life. Hardly anything more unfortunate can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished. He was done. He was almost ready to go to print in his second volume, this big, of the Grundgesetze. And he got this letter from Bertrand Russell, says, all this work that you've done, and you've used basic law 5, and basic law 5 isn't unshakable. I've got this problem. This problem, essentially the Barber paradox. And if you've got this paradox at the very foundation of your development of mathematics, then everything you've done is on shaky ground. You're not going to be able to show that everything that is true can be proven, and everything that you prove is true. You can't do it. So Russell thought he would fix it. Russell decided, I'm going to fix it. And Russell and his colleague Alfred North Whitehead began working on their take on the thing. They tried to avoid that contradiction by using what is called a theory of types instead of just basic sets. And they banned something called impredicative definitions. Like Frege, Russell and Whitehead wanted to show rigorously that if something was true, what is truth? Truth is what we can prove. That's what it is. We're going to prove it. We're going to show you in our book, Principia Mathematica, everything true. We're going to prove it. We're going to use logic. Here's an idea. I just want to show you this picture. It's one of my favorite pictures from Principia Mathematica. This is proposition 54.43. Got a lot of symbols in there. This is rigorously establishing the fact that, well, not quite yet, but this is how you would show that 1 plus 1 equals 2. If we had gotten around to defining addition by now on page 360 of our book. 360 pages in, they still hadn't even defined addition, but when they eventually get around to defining addition, all of this stuff right here is the rigor they would use to show that 1 plus 1 is 2. Well, that's a lot of rigor. If you need that to show you that 1 plus 1 is 2, trying to prove everything. They published 3 volumes of the work, trying to justify everything in mathematics. If it's true, we'll prove it. That's what truth is. Truth is what we are going to prove. In 1931, one of the most important mathematical papers of the 20th century, on formally undecidable propositions of Principia Mathematica and related systems by the Austrian mathematician philosopher Kurt Gödel, who said, you can't do it. Your little goal of trying to show me that everything that is true can be proven, and you're going to prove everything that is true, you're not going to reach it. And here's how Gödel did it. He used arithmetic. He stayed within arithmetic. This sentence that I have written up here in English in Gödel's paper is an arithmetic sentence. It is not an English sentence, it's not a German sentence. He wrote it in German. It is an arithmetic sentence. A sentence in arithmetic that essentially says this. The sentence T asserts that the sentence T cannot be proven. There is an arithmetic sentence in Gödel's paper that says, hey, look at me, I'm a sentence in arithmetic, you can't prove me. Well, what does that mean? That sounds almost like the barber that shaves all the people that don't shave themselves. You got this sentence that says, hey, I can't be proven. Well, is that sentence false? Well, if that sentence is false, so if that sentence is false, it means that the sentence T can be proven. And if you can prove it, it's true. So if it's false, it's true. It can't be false. False leads to this circular thing. Suppose it's true. Suppose the sentence T is true. Well, then we can't prove it. But then we stop there. It can't be false because false leads to a contradiction. So it must be true. But if it's true, you can't prove it. In other words, the sentence T is a true mathematical fact that we cannot prove. Frege and Russell and Whitehead set out to prove everything. If it's true, we can prove it. We're going to prove everything that's true, and Gödel says, no, you're not. Because here's this one sentence, at least one sentence, that is true, that you will never be able to prove. There are things in mathematics, just in mathematics, and most people think mathematics is a paragon of truth. That's where you go to find truth sometimes, it's mathematics. If you want to know something's true, prove it. But Gödel says there are truths about our universe, about mathematics, which is a part of our universe. There are truths that you cannot prove. So what does that mean for math? So we just give up? No. Mathematicians just kept going. There are things we can prove. We just now know that we're never going to be able to prove everything. Even true things. There are some true things that we can't prove. Mathematician Stephen Strogatz has a great quote about the philosophical ramifications of Gödel's theorem, which is, Gödel's theorem is very freeing and liberating because it means that we can't be mechanized and that there is profound mystery forever. There are things in this world that we cannot prove, that are true. So Gödel's theorem leaves us all room for faith. There's no proof of everything. There's lots of room in our lives for things that are true due to faith. It doesn't say that there is no truth. There is truth. It doesn't say that we can't prove things that are true, because we can prove lots of things that are true. It tells us there are true things in our universe that we cannot prove. There is room for faith when we talk about truth. Well, Bertrand Russell was devastated. Bertrand Russell says this: he wanted certainty in a way in which people wanted religious faith. Bertrand Russell was trying to find his fulfillment in mathematics. He said he wanted it so bad, the same way that people want religious faith. And after 20 years of toil working on Principia, he came to the conclusion that there was nothing he could do to make mathematical knowledge indubitable. It just can't be done in math. Math is not a place to put your faith. So how can we avoid, as college students, as academics in our quest for truth, how can we avoid becoming disillusioned like Russell and saying, there's not even certainty in math? And I thought that math was the place where I went. I could either get the right answer or the wrong answer, and that was it. And some things were right and some things were wrong. But we've learned now that there are things in math that are true that we just can't prove. So 1 Corinthians 1:20 and 21, you've heard this verse many times probably. Where is the one who is wise? Where is the debater of this age? Has not God made foolish the wisdom of the world? For since in the wisdom of God, the world did not know God through wisdom, God decided through the foolishness of our proclamation to save those who believe. You're not going to find truth necessarily completely in the world. God decided all of that. That's not where you find truth. That's not where the wise man is. The wisdom of God is to say all of that. That's great, but God, in the foolishness of the proclamation of the gospel, I don't know what just happened. That's lovely. There we go. God decided to save those who believe. So where is the truth? Jesus tells us. Jesus tells us, you will know the truth, and the truth will make you free. Jesus also tells us where the truth can be found. A little later in John, Jesus says, I am the way, the truth, and the life. Ultimate truth is found in God, not in math, not in history or English. Ultimate truth is found in God. It doesn't mean you shouldn't study. God wants us to use our brains to find truths, but just know you're not going to find it in math. There's a proof of that. There's a proof, a mathematical proof that you can't find all truth in math. So don't look for it there. There are true things, and there are things we can prove, but not your ultimate truth. Thank you.